Our next speaker is an ex-mini donut salesman who studied mechanical engineering at the University of Toronto. He spent his post-donut career figuring out how to put electronics in boxes, and his talk will showcase why sheet metal design is worth learning. Please welcome to the Hackaday Super Conference stage, Eric Andersson.
All right, thank you for having me. So, welcome to A Maker's Guide to Designing Sheet Metal Electronics Enclosures. So, who am I? I'm Eric Andersson. I used to sell mini donuts at the Calgary Stampede, the greatest outdoor show on earth, for 5 years. I also studied mechanical engineering at the University of Toronto, undergrad and grad, not as fun. I'm a major rabbit enthusiast, as you may tell from the pictures, and I'm also known to bring Canadian snacks to conferences. And we're coming up on lunch, so come and find me for a special dessert. But why should you listen to me? So my previous job, just after grad school, was as a mechanical designer in the digital signage industry. Now, digital signage is pretty much anything where you have a screen in a box in a public place. So things like mall kiosks, video walls, like that one I did for an airport in Southern Ontario, or retail window signage, like these 2 screens you see here. There's a few hundred of them across the US, some in LA here, some in New York, so on and so forth. I currently work as a mechanical designer for a mobile app testing software company doing hardware because we test apps on real phones. So we have to rack mount phones, and it's my job to figure out how to do that. So I design high density cell phone enclosures for them and various other computer bracketry things. Lots of sheet metal involved in both of these worlds. So what are we going to talk about today? I'm going to compare sheet metal to some other common manufacturing processes. I'm going to tell you how sheet metal actually works, the fabrication process, a little bit of basic sheet metal design, and some low volume sourcing. And by low volume, I mean pretty much anything from 100 down to 1. The context of this is going to be like with North American standards, sourcing, materials, nomenclature, and so on and so forth. What are we not going to cover? Because there's a lot in the world of sheet metal. We're not doing anything high volume in terms of manufacturing. I'm not getting into any of the really, really technical details because they're just way, way too much. It's a whole science. No advanced design or CAD discussion, really. And nothing DIY, unfortunately. I don't have that much experience on it. Maybe in a future talk, we'll see. And nothing about like the global standards or sourcing, unfortunately. So let's start with an example, a project. We want to make a thing. How about the new Raspberry Pi 5? We want to mount it to a TV, perhaps, or a computer monitor. Let's say something with a VESA 100 by 100 mounting system. Most monitors have that. We want some active cooling. Let's throw a 40 millimeter fan in there. We want to have room for some expansion boards or hats. We want to have some cable management, of course, both inside the enclosure and on the outside. We want it to be pretty strong because it'll be mounted to a TV, perhaps in a public place. We want it to be strong, both physically and in terms of thermals, like temperature. And I've decided that off-the-shelf solutions aren't quite there. Most of them do many of these things, none of them do all of them, so we're going to make our own thing. Now, 2 common options that people use in like the maker community to manufacture are 3D printing and CNC machining. 3D printing is nice because complexity is pretty much free. We can all do it in our houses. The problem is when you get to more engineered materials like nylon and so forth, they get really, really expensive, both the materials and the printers. CNC machining is nice because you get a really nice, pretty, shiny machined part, and it's super precise. The problem is as you add feature count, the prices balloon like crazy. And not only that, because it's a subtractive process, and this is particularly bad for enclosures where they're mostly air, you have to pay for a big, big block of material, and then you have to pay to remove most of that material on the machine, so that adds up to a lot of money. So with 3D printing, I found this case on printables.com, threw it onto an online website that does HP multi-jetting nylon printing, and I had the option of either white as out of the printer or dyed black, and like, okay, that's fine. One of them will cost $120 US. We go up to 50, we get down to $30, not bad. 1 week lead time, not the worst, but maybe we just need it to be made out of metal. So we go to CNC machining. With the same company, I whipped this together quickly, this model, made it out of aluminum, and with the as machine finish, no bead blasting, like nice satin finish, no anodization, right off the machine, about $500 US for one, and then up to 50, you're down to 60. 2 week lead time. If you go overseas with the same options, Price cuts in half, but your lead time triples. So not the best. Enter sheet metal. It's pretty much origami, but with metal. You cut a flat sheet and you fold it into shape. Long story short, talk done, right? Well, there's less material, there's less processing, and that means less money out of your pocket, which is great. And because of that, the way sheet metal works, where you're folding, the cost mostly scales with the surface area of your enclosure, not the volume, which is great. So this is a part I made where we've got 3 parts. We've got a base, a lid, and an adapter plate with tons of slots to be extra compatible with not just VESA mounting, but other options. One of them, about $70, and then up to 50, we're down to 23 US dollars with a 1-week lead time, which is pretty great. But how did we make it? I'm going to focus on this, the base part of the case, because it's got like the most interesting features, got the most processes involved. It starts in CAD, unsurprisingly. Pretty much any 3D parametric CAD package will be able to do sheet metal, SolidWorks, Fusion 360, et cetera, et cetera. Just make sure when you're using those CAD programs that you're actually modeling with sheet metal features, because there are a lot of features that the CAD can do that you're going to need for manufacturing, like flattening and so on and so forth. I use Fusion 360 for this one. So the sheet metal manufacturing process is these 4 main steps: cut, bend, fasten, and finish. So let's start with cut. So we take our 3D model, we use the flatten feature in our CAD, we get a 2D DXF. And this is very similar to laser cutting, say, acrylic, wood, what have you, on a desktop laser cutter. The only difference is these are laser cutters the size of a shipping container that have tens of thousands of watts. And they can cut really, really thick, thicker than you'd ever need for an enclosure, like inch plus metal, which is pretty great. What kind of materials are you going to cut out of? The default is pretty much just like regular steel, mild steel. If you're a little cost sensitive and you don't want to pay for like any finishing processes, you can go galvanized, which is just the regular steel, but with a zinc coating. And you'll see some on HVAC parts, for example, anything with that shiny, like silvery pattern on it. A lot of computer parts, anything internal that's not cosmetic, often galvanized steel. If you really, really care about strength to weight, go aluminum. If corrosion resistance is really important, or like maybe food safety, go stainless. All these materials come in standard thicknesses, and they're referred to in North America by different gauges, similar to wire gauge. Lower the gauge number, thicker the material. Keep in mind, though, for like any numbered gauge, the thickness is going to be a little bit different for each material, so keep that in mind. Step 2, you're going to bend. So we take the flat pattern to our press brake. We push it on against the back gauge on the die. The tool will sink down into it, creating that fold that you can see in the GIF. And this is how the case was made. There's a little simulation. You can see all 4 folds. Notice how the tooling does change width because the bends are not the same width. This is a rectangular shaped case. So kind of interesting right there. In case the animation doesn't work, or if you're reading a PDF later, there you go. So why do we add these bends? The obvious reason is because, well, you design them in there because you want to like enclose something, you want to add, you want to hold some parts, something like that. The other reason is stiffness. Now, sheet metal is a sheet product. It is very thin and it can be a bit floppy by itself. A lot of bends that you think aren't really doing anything are actually there to make it stiffer and stronger. The stiffness of a part, the resistance to bending, is driven by the geometry of the entire part and not just the sheet thickness. So I have 2 parts here, 50 millimeters wide, 1 millimeter thick. If I wanted to make the left piece stronger, I could double the thickness to 2 millimeters. That'd double the weight, and it would make it 8 times stronger, roughly. But if I stick to the 1 millimeter and add these 2 5 millimeter bends on each end, you're only adding 20% of the weight, but it's 14 times stronger than the original piece. So geometry is really, really, really important. And here's a great example. Most auto body panels are less than a millimeter thick, and there's a reason that cars are round and bulbous and that they're never, ever, ever flat. Well, usually, and that's because of stiffness as well as aesthetics. Yeah. So here are some of the common bends that you'll see out there. There's more than this, but these are like kind of the more useful ones. The flange bend, or it's kind of like a normal, regular bend. You're just bending the edge of a piece of material. It doesn't have to be the full width of the material. You can see on this one, one end is closed. The window bend, the next one, is pretty much a regular bend, but it's going from inside the material, and it leaves like a window shape, hence the name. A hem is pretty much take a flange bend, keep going, keep going, keep going, and then crush it. It's good for a little extra stiffness, for very little gain in thickness. It's also good for if you want to like round over an edge so it's not as sharp for when you're contacting it. You can even take 2 hems of 2 parts and like interlock parts if you really want to. The U-bend is actually just 2 flange bends. The reason I mention it, it's very common to make that shape, and there's a ratio of the width and the height that you need to keep in mind, because if your height is too great, then you can crash into the press brake when you're bending. The fabricators will tell you what that ratio can be. Step 3, we got to fasten the parts together. We just have a bunch of bits of metal. We got to attach everything to each other. With this case, we put some press fit nuts, or self-clinching nuts. They're little nuts that you put onto the press there. Uses a couple tons of force to just smush them into the material. We do this because if we tapped this, and these are M3 threads, in 1 millimeter, 1.2 millimeter material, we'd have like 2 and a bit threads, which is like not enough. These nuts add like 4 plus, which is pretty great. There's more than just nuts though. They do tons of other pieces of hardware. PEM is the biggest brand. They're kind of the Kleenex of the world. Like most people just refer to these as PEMs regardless of who makes them. They make standoffs, studs, all sorts of things. And I actually have some samples with me that you can come take a look at later. Some important specs that you should know about these pieces of hardware. Everyone's going to have a minimum sheet thickness to work. A lot of the common ones, like the nuts and standoffs, it's like 1 millimeter. Everyone's going to have a certain like cutout because you're inserting it into a hole, shape and size. And also there's a minimum distance that these need to be from the edge of a material or a bend, or else the pressing process won't be full strength. You should verify with your fabricator what parts they stock and what they're capable of installing. Other options for removable sheet metal parts, sheet metal screws. This is the cheapest way because you don't need any of the attached hardware, so you save that process in manufacturing. But the problem is it's not very reusable because there's very little thread. Rivet nuts are similar to the clinching nuts, but they grip from both sides, so they're stronger, but they're usually bigger as well. And because they clinch from both sides, you don't get a flush face on the outside. Weld nuts they can be spot welded on, similar to how the clinching nuts work, or they can actually just be MIG welded on. They're the biggest by far, they're strongest, but it can be expensive, and for electronics, almost certainly overkill. Now for permanently fastening sheet metal parts together, we can use blind rivets, for example. You can just buy those at the hardware store. They're vibration resistant compared to your standard threaded fasteners. There's no heat involved in the process, so no worries about distortion or anything like that. But they have a hollow shaft, these blind rivets, so if you need something to be waterproof, for example, probably not the best option. You can spot weld. Most sheet metal fabricators can do that. It's very low profile because you're not adding any material. It's pretty much permanent, or it is, and there's no holes, which is pretty good. But it's not quite as strong as like full bore, like MIG or TIG welding, which is by far the strongest, but it's also by far the most expensive. It is really, really, really expensive to weld sheet metal or have a fabricator do it. Also because of the added heat through the welding process with very thin gauge materials, you can get some distortion. So I generally try to avoid welding as much as I can, and if I do have to weld, I try and do it in a way that it can be spot welded. Finally, we have adhesives like glues, tapes, things like that, VHB tapes, so on and so forth. That's mostly used in the signage industry because they care a lot about cosmetics and aesthetics. And the good thing about adhesives is that like you can use them without any holes or no added heat and so on and so forth. It does add thickness though, depending on the tape. Some of them can be quite thick, like the VHB foam tapes. But they're a good option for something where you really, really care about aesthetics. Finally, we gotta like finish the parts. We have like raw metal. We want to make it look good. All these finishes will help prevent corrosion, enhance the appearance of the parts. The most common is powder coating. There's unlimited colors under the sun, various textures. You can get glossy, matte, sand texture, so on and so forth. When you're designing, though, keep in mind that they do add thickness, anywhere from 3 to 5 thousandths of an inch of thickness. So you'll have to adjust your CAD files to compensate for that. You can plate your materials. The problem with that, of course, it doesn't really change the surface look that much. It'll kind of change the color. It's better for like corrosion prevention. But if there's flaws and so on, they'll still be there, so you'll have to do some pre-processing like bead blasting or sanding. If you have aluminum, you can anodize it, and that looks cool. Everybody likes that. Stainless steel can be passivated, so that's just removing the free iron off of the surface to prevent like corrosion. You can paint your parts, but honestly, why bother when powder coating is stronger, more durable, and not terribly expensive? Or you can just do nothing. If it's a prototype part, if it's an internal part, and you don't care if there's a little bit of rust on it someday, yeah, do nothing. Or if you're using galvanized steel sheet, well, it's already finished. It's been galvanized from the factory, so problem solved. And that's exactly what I did with our example project, which is why I don't have a slide for it. So there are some design limitations. We can't just do anything under the sun with sheet metal. The bending process involves the tool and the die, and it contacts the sheet at 3 points, those orange circles. And those drive the inside radius, which is what you'll choose when you're designing your parts. And more importantly, it contributes to the minimum flange length that you can do. That's that blue line. If you make your bend shorter than that, it won't contact the die at the correct spot, and you can get distortion. And sometimes it just won't bend at all. It really depends on the material, thickness, equipment fabricator, and so on and so forth. Ask your fabricator, and they'll have like a list for each material. We can do this radius and with this minimum bend length, and so on and so forth. There are tolerance limitations. Laser cutting is like accurate to about 5/1000ths of an inch, just the flat. You start adding bends though, your tolerances stack up. The length of the bend, depending on how accurately they place it, that'll add some tolerance. The angle of the bend itself, gonna add a little more. So when you start stacking things up, it can get pretty wacky. So consider that in your design. You can do things like turning circles into slots, or just try and avoid having important dimensions across multiple bends. Again, confirm this with your fabricator, they'll have lots to say. For integrating electronics, we can use the PEM standoffs that I mentioned earlier. They're great because they're permanent, they're electrically conductive, so you can ground stuff, and they're flush on the front side, which is good too. But if you can't do that, or if you don't want to, you can use things like plastic board and cable supports, like nylon standoffs. They're nice because they're removable, so you can change them. They're non-conductive, so you can insulate, but they're not flush because they're always going to go through a hole or something. You can use like regular threaded hex standoffs, but I don't like them. So we want to make the thing that we've designed. The normal way that you source is to contact a shop, do the classic sourcing routine, and just hope that they're interested in your very, very small project. Wait for the quote, wait for the production. It's a whole lot of back and forth. It's still worth doing, if you're working on a very big project or if it's a very complex project where you need to really tie into their manufacturing limitations. But for like small scale prototypes, it's not fun. But today we have the internet. So there are online suppliers, just like how PCB buying got so much faster, cheaper, easier. Same thing with sheet metal now, very recently. There's no minimum quantity usually. The quotes or prices are fast or sometimes instant, and ordering is very easy. They love taking your money. All you got to do is upload your files, configure the parts, give them the money, and then ta-da, they'll show up a couple weeks later. I have 3 example suppliers, Protocase, Sendcut, Send, and Oshcut. There are more out there, but these ones specialize in sheet metal. And I have a real example of a sourcing exercise I did. I ordered some parts just over a week ago, last Thursday. They bent them on Friday. They did the hardware on Monday. They did quality the same day. They shipped them on Tuesday. It arrived Wednesday. And I installed it and put it together yesterday. And it is actually the example project that we worked on in this exercise, the pie case. So you can come take a look at it later. It all came together, thankfully. Pretty fun. So the 3 options. We have Protocase. They're a Canadian outfit. They're the premium option. They're essentially a full-scale fabrication sheet metal shop. They do every process you need. And they have engineers on staff that can help you with design, so on and so forth. However, they have setup fees, and they charge for the engineering time as well. So it can be quite expensive if you have a very, very small project. And their instant quoting tool isn't the best. You often have to wait 24 hours for a quote, which is still fine. They're Sendcut Send. They're in Nevada and Kentucky. They don't do quite as much, but their instant pricing is truly instant. In fact, as you build a part, you will see the price change, and you can see the volume discounts, which is awesome. Free shipping in the US, $20 to Canada, I think. Not quite as flexible as Protocase. And you have to upload 2D files and then add the pens in, which is kind of annoying. Oshcut, I haven't actually ordered from Oshcut yet, but they're really, really cool. I like their website. In fact, the simulation you saw earlier was a screen capture of their quoting tool. You upload a 3D file, and they'll just configure everything. All you really have to do is say what material you want and if you want it powder coated or not. They even do tube laser cutting, which is really, really hard to find. Things like square tube, round tube, rectangular tube, laser cut with all sorts of patterns, really cool. The big downside, number one, they only ship in the US, so being from Canada, I've never been able to order from them. And they don't have any PEM hardware, the self-clinching hardware, which really, really grinds my gears, and I hope they have that soon. So who you're going to choose. If you're starting with very, very basic, simple parts, go with Sen because there's no setup fee. If you don't need that self-clinching hardware and you just want to upload a 3D file, Oshkot's the way to go. If you've got something really, really complicated and a lot of features and you need to verify that, say, a full assembly works, Protocase is the way to go because they have engineers to review your files. If you're really good at CAD, though, and you know that you've toleranced everything correctly, you can actually go back to Sen because, again, no setup fees makes it quite affordable. If you're not in North America, Protocase is the only option of those three that ships globally, or find a local option as well. And again, if you have a really, really big project that's very complex and you want to like push the limits of the manufacturing processes, do the local thing, build a relationship with a shop, or you can just try them all. So there's further reading out there. You can do CAD tutorials, they're all good. Lots of courses out there, lots of good articles. Sheet metal is a very mature field, so there's lots of information online. Even Hackaday has a post. Backblaze, the storage company, they published the full step files for a rack-mount storage server that they designed, and there's a lot of good learning in that if you open up the step files and see how they made all those parts work. So what have we learned, or what have I hope you learned? We've learned sheet metal is affordable, it's versatile, it's accessible, the barrier to entry is lower than it's ever been, and it's worth learning, or I hope you think it's worth learning, and there's a lot of fun things you can do with it. So that's it. Thank you for listening, and that's how you can get in contact with me. I've been told that because we're running late with lunch, I won't be doing Q&A up here, but you can find me out there throughout the rest of the con. I'm going to have this with me and the samples. So yeah, that's all. Thank you so much.